So part two. So now we're going to try to cover the last two rock types in as quick a manner as we can. And so just like the first version of the PowerPoint, I'm trying to run through some really basics of sedimentary rocks and metamorphic rocks without getting too much into the gory details. Now look, a sedimentary rock in general is something that's composed of fragments or pieces of pre-existing rock. And those are transported by water or wind, and then they settle out and they form layers. Over time, the burial of those pieces can get cemented together and we can form a sedimentary rock. We can also form them through chemical processes. But the idea of having pieces glued together would kind of be like a sandstone, right? So think of sands, like a beach. We deposit that sand as being weathered. It's being brought to the coast and it's being buried. Over time, those pieces get squished together, water flows through them and can act like a cement and glue them together, and voila, we get sandstone. So there's two different ways that we can break down existing rocks, and that's either mechanical or chemical. So mechanical is like a physical breaking, right? We take a hammer, we smack it, it cracks. That's mechanical. And chemical means that there's some chemical reaction occurring to the minerals that are in the rock that are causing it to either dissolve or break. Okay? And then the terms erosion and weathering, when we talk about geology, right? Weathering is this process, mechanical or chemical, breaking the rock. Erosion is actually the physical removal, transportation of the material. So try to use those correctly when we can. Okay, so the usefulness of both mechanical and chemical together is the idea that chemical processes can only affect the things that it can get to. And believe it or not, water is a really big, what are we going to say, solvent? No, it can dissolve rock. It can break it down over time, which doesn't seem like it should because water seems pretty inert, but it does react with certain minerals that are present in the rock. And so the idea of mechanical weathering is I take something like this and I break it. And now I expose more surface area for fluids and water to move down, and then they can use the chemical processes to break down the rock. And then we get them even smaller. So the more we break it mechanically, the more that chemically it can be broken down, and that just keeps a cycle on top of itself and keeps going and going, and that can speed up the process of making really big pieces of rock into really small pieces of rock. So how do we mechanically weather the rock? Okay, so one of the main ways we do that is with what's called frost action. So anywhere where there is a temperature change and water, we can get frost action as long as the temperature gets below freezing. And so in a lot of places around the world, water will move into small cracks or fractures in the rock and freeze. And when it freezes, it expands. This is the property of water. And so the idea is that the expansion of the water when it freezes doesn't miraculously crack the rock into millions of pieces, but it's a slow process that occurs every day or even seasonally, but over hundreds of thousands of years. And so that constant pressure of an expanding material in a fracture weakens it, and over time it'll eventually break and fracture. Okay, and so once again, geology is about time, and so we can break things up with these really minimal processes if we do it enough and do it for a long enough period of time. And so over time we can get things that look like this, like Bryce Canyon. And so another way that we can cause the rocks to mechanically break down is for thermal expansion and contraction. So, all right, so you didn't like the frost action story because we live in Phoenix and it's hot and it rarely freezes and we don't get any water. So what we would say is happening here in a lot of places is the rocks that are exposed to the heat are changing as the heat heats them up, right? So they expand when they get warmer. And for certain rocks, like we'll take granite, which is a igneous rock that is made up of multiple minerals. And so the idea is that each mineral has its own property, and one of those is how it reacts to heat. So one mineral expands a little more than the other, and there's pressure being placed on these mineral boundaries where they touch each other. And so over time, that pressure, same thing, do that enough times, do it for a long enough period of time, and that pressure causes a crack to form. And that crack then grows, and then miraculously, if it ever rains, right, that can dissolve a little bit, make it bigger. If we do it for a long enough period of time, we can cause the rocks to break down. Right? Time is your friend here when you're a geologist. The other thing we can do is something called pressure release. And this happens for specific rocks that have been buried deep in the earth. So one of the things that we talk about in igneous rocks is there's certain rocks that cool and crystallize at depth. We give the term to a very large body of magma that cooled and crystallized at depth. We give that term batholith is the name of the feature. But the idea is that in order to get big crystals, it has to be buried several kilometers deep to insulate the magma so it cools slow enough to form big crystals. But over time, this land surface can be uplifted through processes like plate tectonics, and all this material gets eroded away. Well, this material has a lot of pressure that's pushing down on this. As we release the pressure, this material wants to expand. And so over time, it expands, same thing. The pressure is great, it fails slowly, same thing. As we remove the material on top, it doesn't just spontaneously break into a million pieces because the rock is strong, but it's under stress. And that stress over time can cause failure along mineral grains and things like that, weaknesses in the rock. They start to crack and pop. And we slowly get features like this that are related to this rock being buried at some time in its geologic past. Some other pictures there, some pressure release stuff. We can get rocks broken down by organic activity, roots and critters. Yeah, I know it seems like a small thing, but you know, have trees grow in the rock for 10,000 years, you can cause some damage with that, right? So it's the same thing. It's a time thing. And of course, there's a lot of trees with roots and a lot of critters that can, you know, work their way through material. All right, let's see. We've already kind of talked about this, so I'm going to blaze over that. And I'm going to blaze through this chemical weathering too, but the idea is that certain rocks react to water in a more profound way than others. And so we know that some rocks, like a limestone, which is made of calcite, which I introduced in the first video, reacts to water because water is slightly acidic. And as the water lays on the rock or moves across the rock, it's going to dissolve the calcite mineral that's there. So over time, it can actually eat away at the rock and cause some of the features you see here. And so it's dissolving some of the material. And so, you know, CO2 and water can form an acid. It's not super strong, it's weak. And so carbonic acid is not going to, you know, dissolve away your skin or anything. But it's a time thing. Once again, it can dissolve away some parts of the rock and certain minerals. And then that's a weakness in the rock, and then it can crack and break and get bigger. And so we want to talk about, you know, limestone because, of course, it's a hazard for sinkholes. We talked about caves and things like that. The ground surface sinking or not being strong enough to support things. We want to know something about how that affects rocks, right? And some of that is just fluids moving through the rock, and it's dissolving some of this material away. We just throw in this oxidation thing because, yay, it's Sedona. And why are the rocks in Sedona red? It's because there's iron in some of this material, and the iron has oxidized, almost rusted, if you will. And that's how we kind of identify that this must have been formed on land where there was air, oxygen exposed to it, and so it rusted the rocks, if you like. But that's kind of why the material here is red in Sedona, is because of oxidation, which is a chemical weathering process. So I'm going to let you look through some of these slides, but I want to try and get through to the other two rock types. This is just telling you about strength and stability of certain rocks. We can look at those. And so when we want to talk about sedimentary rocks, all that material we just broke apart in our weathering story has to go somewhere. And almost always it's moving down slope somewhere. So from high areas to low areas. And so the mountains are being weathered and then eroded and deposited in these little things called alluvial fans, where we have a rush of water deposit a bunch of stuff on the valley floor. Rivers are transporting stuff and they flood and they deposit stuff. The rivers take stuff all the way to the coast and they dump stuff here at the beach. And that material gets moved by the oceans and that gets down here. So we have these different areas where we can deposit material, and based on where they're deposited, a lot of times we get specific rocks, and then we can identify their environment, which can be useful to tell us something about the story that has occurred over geologic time. So, the sedimentary rock story, holy cow, here we go. So, pieces, fragments that get moved by water or wind get compacted over time, and as fluids move through these little pieces here, the water has usually either some silica or some calcium carbonate dissolved in it, and it precipitates out as a crystal, and it actually glues these pieces together, so it cements them. And so if these were sand grains and then they got deposited on the beach from, let's say, a river, and then over long periods of time we deposit more and more and more, so there's a lot of material on top of this, it squishes these down, water percolates down through here and eventually cements it. That can turn that into, let's say, a sandstone if these were sand pieces. Okay? And so the story of sedimentary rocks is there's really two groups. There are what we call clastic, which is made of pieces of other rocks that have been glued together. And how do we identify those? We look at their size and shape of the pieces to tell me what I have. The other version is that chemical version I mentioned, where we look at what it's composed of, what its chemical composition is to tell us what we have. So in this example here, we use a size designation: gravel, sand, silt, and clay. In geology, we can use these as sizes. If it's gravel size, it's either going to be called a conglomerate or a breccia based on the shape of the pieces. If it's sand size, like a beach sand, we're going to call it a sandstone. And for us, if it's below sand, we're going to group that all as mud and just call all that stuff a mudstone. So there's really just four: conglomerate or breccia for the big stuff, sandstone, and mudstone. Okay, and that's all we need to kind of figure out for our sedimentary rocks that are made of pieces. Okay, now same thing. I'm going to let you look through these slides. They just talk about the sizes and where the breakdowns of the different sizes. We also said we want to look at their shape because that can tell us something. So only when they're big, when they're gravel size or sand size, we can identify their shape. And the story usually is that if they're rounded, it suggests that it was moved far from its source and probably water was involved. If they're angular like this, it means that they did not travel very far, because if they did, these sharp edges would have been worn away. And so once again, with all rocks, we want to interpret the environment they were created in, because then that can tell us something about the history of the area, of course, and then maybe we can read into it some of its properties, and that might play a role in a hazard that we might want to identify. We can talk about sorting. It's just how the pieces, are they all the same size or different? We can look at what's the different pieces that are caught up in my rock. That can tell us something about its history. And we also said that, remember, the size and roundness of it can indicate how far away it is from the source. Big angular pieces, they didn't go very far. The really small pieces, they went pretty far. What else? Okay, so real quick, we're going to talk about the rock names, right? Big means gravel size. Any piece that's gravel size. Doesn't have to be all of them. If it's angular, it's a breccia. If it's rounded, it's a conglomerate. This suggests water moved a pretty fair distance because it rounded. This is like a landslide deposit. These fragments did not go very far from their source. And so one possible depositional environment might be a landslide of some kind. Sandstone, right? So that's just rounded pieces. You pick it up, you look at it. You can barely see the pieces. It kind of looks like beach sand. Now there's a variety of other sandstones. We don't care. Right? For this class, we just want to note that a sandstone is made of sand-sized pieces. The most common type is that the pieces are made of quartz. And then the mudstones, okay? So these are the really fine-grained stuff. What we want to know about mudstones is they're fairly weak. They break, they weather, they fracture pretty easily. And so we want to take that into consideration when we're identifying hazards. Then our second group, so those were our clastic. We've got our chemical ones. And so all we're looking for here is what are they made of? So we need to do a test. We find a rock. We can look at it. We can't see any pieces, but it looks like there might be some crystals there. So what are those crystals made of? If we can figure out what those are, we can name it, then we'll know some properties about it, and then we can evaluate it. And so some common things, there's a bunch, but we're not going to get crazy, right? We just want to know the basics. Carbonates are the big ones for us. Why? These are the limestones. These are the rocks made of calcite. When water gets on them, it slowly dissolves them. So this is our hazard of sinkholes, where we have limestones that are dissolved over geologic time, forming cavities that can collapse. We can have the land surface sink down over time, and so this is something we want to identify. How do we know? Well, in the field we use diluted hydrochloric acid, and it causes the rock to fizz, indicating that it's calcite. If it's a sedimentary rock, I'm pretty confident that's a limestone. Chert, we're going to skip over, but it is just a quartz deposit. It isn't really related to hazards very much, but it is a rock that is chemical and made of quartz. Evaporites. We care about evaporites for a similar reason we care about the limestones. This is the idea that they're very soluble in water. We don't want layers of gypsum and limestone at depth if we're going to build on it or attach to it in some way. So we have to be concerned about identifying these. So of course halite is salty, but the water will dissolve it, so that can be an indicator. And so that's why we care about evaporites. So look, just like with igneous rocks, what you would do is you would use a chart. And once again, there's a variety of charts out there, but they all are relatively similar. The two groups here are either clastic, made of pieces, or chemical. So if it's made of pieces, it's either really big, looks like beach sand, or you can't see them. And so really big, it's either conglomerate or breccia, just based on the size, the shape of the pieces. If it's looks like beach sand, it's a sandstone, and if we can't tell it, for us, it's a mudstone. And then of course, if it looks like there's crystals or we can't see any pieces, we do a variety of tests on them. Halite tastes like salt. Calcite will react to acid and fizz. Gypsum can dissolve too. So really for us, we just care about halite, gypsum, and calcite. Those are ones more related to hazards than the others. And so these are the sedimentary rocks we'd like to be aware of and be able to identify and know something about them, right? The idea that the calcite, the halite, and the gypsum are weak, and that the clastic mudstone is probably the weakest of these here. So if we're going to build or look for things that are weak, those are the things we want to identify. And finally, the good news is metamorphic rocks are really fast and furious, so there isn't a lot that we want to mention about those. There's just same thing, some groupings here. And so if we go through this really fast, what metamorphic rocks can tell us is what's happened at depth. And so a metamorphic rock is a rock that has been altered by heat, pressure, and fluids. And almost always this is happening deep inside the earth. So the rocks are buried deep for some reason, and that extreme pressure and heat changes the rock from what it used to be into something else. And then we want to look at it and be able to identify that. And so it's either pressure, temperature, or fluids, but in general, it's a combination of almost all three always. It's just whether one dominates over the other. And so, same thing, we're going to blaze through this a little bit. So here's our main causes of metamorphism. And the idea is we have temperature and pressure, And so we have different types we can look at. For us, we really just care about two types, what's called contact metamorphism over here, which is high heat deformation or change, right? And high pressure types of change or metamorphism, which we're going to refer to as more regional metamorphism. And so if we have a high temperature, it's for a variety of reasons, but in general, it's because magma, molten rock at depth, is interacting with the rocks. And so in some parts it's molten, but it can't melt everything, and so it bakes or cooks or alters the rock right around it. This is what we would call contact metamorphism. And this basically just recrystallizes the material so it looks very crystalline. And so in order to identify a rock that has been baked, you usually have to do some type of test to identify what it's made of. And then that can tell us what type of metamorphic rock we have. The other way is pressure. So if heat isn't driving the change, it's pressure, but it's not this confining pressure which squishes things in all directions. It's what we're going to call differential pressure. It means that in one direction it's much more pressure than the other. And the reason that we identify it that way is because that pressure causes the rocks to change in a unique way. What it does to certain rocks is it realigns elongated minerals. And so in this sample here, there's these little lines that represent elongated minerals that are randomly oriented. But under huge confining pressures, they actually rotate without melting, and they line up and they form this layering almost that you see. And we give that a term, we call it foliation, which means the lining up of these elongated minerals. If we see that, we would argue that pressure was probably the dominant force here causing the change, and we would call that regional metamorphism. All right, so fluids can also and almost always are involved in probably all of the metamorphic processes, just in some places it's more fluids than others, but almost always fluids are interacting and causing some change. So let's be clear, pressure, temperature, fluids are always causing metamorphism. It's just what's really dominating. And for us, we really just care about these two types here, regional and contact. Right? Contact is high temperature driving the change. Regional is, even though there's high pressure and temperature, it's the pressure that's doing the changes. Right? So what we see is contact is because a magma body probably intrudes into existing rock and bakes it. Regional is usually from a convergent plate boundary where things are colliding into each other, and that means there's a huge stress, right, that's happening horizontally, squishing the rocks. And at depth, that can cause, because it's hot enough, the minerals to rotate and form a texture that we would call foliation. All right, so I'm going to blaze through some of this stuff here because it's not as important. It's really just reviewing some of the things. This foliated texture is related to regional metamorphism. And in order to identify metamorphic rocks, we would look for that texture. If we don't see it, then we would argue that the temperature must have caused it to be metamorphosed, and we would look at something about its composition to figure out what we have. So the reason that we don't focus too much on metamorphic rocks is because they're all fairly strong. When they've been subjected to this heat and pressure, they usually get stronger, but there are some rocks that are foliated because there's some lining up of these minerals that makes that surface a little bit of a weakness where they're kind of all aligned and layered. They can fail along that layering or foliation. But other than that, we would argue that mostly the metamorphic rocks are pretty stable. And so if we look at, I'm going to once again kind of jump through, and the idea that when you're identifying metamorphic rocks, you're looking for texture. Foliated or non-foliated. Here's non-foliated. This is a metamorphic rock. There's no layering or lining up of minerals that I can see. So this must have been cooked. and then I can use a test to figure out what it's made of and then give it a name. If it's been created by high pressures, it's going to have layers. Now look, this looks almost like a mudstone because it's very similar. It is layered. We're looking at the top, so it's these thin layers. This is caused by forces crushing this material from top to bottom and aligning the minerals. This is what's called foliated. And so we would name the rock based on its degree of foliation. Here we call it a slate because it's a pretty low-grade metamorphism. Then as it gets more defined and the minerals get larger, we would give it other names. In this case, this is what's called a phyllite. Still foliated, still high pressure, differential pressure causing the change, still regional metamorphism. A schist is another foliated regional metamorphic rock. And then a gneiss is kind of the highest grade metamorphic rock that we see, and it's usually identified by this light and dark banding. Suggested that in this example here at the bottom left, that the pressure was coming from the top and the bottom, and it was compressing that, and it caused all the minerals to rotate and differentiate like that. This would suggest a very high grade metamorphic event related to regional metamorphism, which we usually relate to some type of subduction event. And then, like we said, if we're trying to figure out what the rock was, we would want to look at its composition, because whatever the rock starts out as before it was metamorphosed is going to be an indicator of what it's going to end up as. Some rocks, when we metamorphose, they don't change very much at all, and they're hard to ID. Others change more significantly. So there's a bunch of names here and stuff. I don't want you to worry about this one here, but there's this idea that we can find little minerals, and that's what this was. Occasionally we can get these little minerals that show up during metamorphism. These only occur at pressures and temperatures deep inside the earth, and so then they're an indicator of where this rock came from. Let's see, what else? Talking a little bit about, if we take a sandstone and we cook it, we get a quartzite. We take a limestone, we cook it, we get a marble. These are both contact metamorphic rocks. If we're looking at our foliated rocks, they're usually either mudstones or granites that get crushed and turned into these. And that's because these minerals, or these rocks, have these elongated minerals in them that can line up, that can give me my foliated texture. So just like before, you're given a chart. You want to use the chart to figure out what type of rock you have and maybe a little history of what's going on there. So if it's foliated, we look at the low-grade metamorphism where you can barely see the foliation. That's a slate. Up to a high-grade metamorphic rock that's foliated would be a gneiss. The ones down here are all non-foliated, and for us, we're going to argue that those are mostly just contact metamorphism, which means high heat. We really only talk about quartzite and marble because they relate to sandstone and limestone, which are super common. And so those are the ones that we'd want to be aware of. But once again, these rocks are pretty stable. Maybe only kind of these in here would be a little less stable because of their foliation, but not as a big deal as some of the other rocks we've discussed. Okay, we finally made it, I think. Here's the rock cycle once again, just shows the relationship to everything we've covered. Two types of igneous rocks. We have intrusive and extrusive. We weather stuff, doesn't matter which one gets weathered. We erode it, transport it, deposit it, lithify it, which just means turn it into a rock. We get sedimentary rocks. If we keep burying them deep enough, the heat can cause them to change. We keep heating them, they melt, they're magma, goes back here again, and all over the place. It's crazy. Okay. Hopefully that's not so much that your head explodes. Lab's going to go over some stuff too, so you'll have some reinforcement through that. Any questions, please contact me.